Good day to you. My name is Omnia Sarhan. I am a student of Texas A&M University in the Department of Electrical Engineering. So today I'm going to be explaining one of the papers on large language models. It is called Leveraging Large Language Models for Predictive Chemistry. So let's go into the table of contents first. So basically, these are the topics I'm going to be talking about today. So I'm going to start with the introduction. So here we are talking about the potentials of large language models. So researchers have found that they wanted to test one of these large language models called Generative Pre-trained Transformer 3, which is GPT-3 model in chemistry. So basically, the study is going to be about understanding and evaluating the GPT-3 capabilities in predicting chemistry and designing novel molecules. That is because since we know that LLMs, which are the large language models, have demonstrated the ability to generate coherent text code and even perform simple regression and classification tasks, basically the researchers wanted to find out how they would also perform in chemical properties and designing novel molecules in chemistry. So in that case, when we ask what is the significance of such study, we are saying that it would revolutionize the chemical research by providing tools that we could use in the major of chemistry. So basically, we first talk about the state-of-the-art methods. So these state-of-art methods are the methods with which the researcher is actually comparing his large language model and its performance. So basically, you will see that the researcher here divides the baselines into two. So we have the pre-trained and then the not pre-trained deep learning approaches. So in the pre-trained, we have different types of deep learning methods. We have graph neural networks, and we have material optimal descriptor network, and then we have attention-based network, and we have transformers. On the other side, we have XGBoost, and we have random forest, and we have MatBench, which is actually a network that is designed specifically for computational chemistry. So basically, after reading the state-of-art methods, we actually find out that the research gaps are actually the fact that most of these models cannot interpret abstract molecular representation. That is because we have a lot of different molecular representations out there in chemistry, and these models have limited ability to absorb all these different representations. Another thing is it has some issue in extrapolating beyond the training data. That is because since it is not able to understand the text and the coherent data given, it has some issue with the extrapolating in chemistry. And then also another factor that it is time consuming and computationally expensive because it requires a lot of data points, and it requires a lot of training time and training resources. Now we go into the proposed method, which is supposedly utilizing the large language model that is called GPT-3 in order to predict chemical properties and design novel molecules. So basically, the researcher here is trying to close the gap by first, he's going to be fine-tuning the GPT-3 model and testing it on different tasks, which are going to be talked about later on. And then he compares the performance of the model with the baseline methods, and then he checks the validity of these results by stretching the limits. So now we talk about the steps taken in the methodology. So first we said fine-tuning, which is about updating the weights on task-specific dataset. That is one. And that is by giving the model some questions and answers to fine-tune these weights. Secondly, we have another task, which is the classification. So we train the model to predict molecules, property of molecules, materials, and chemical reactions. And then we have a regression task where we train the model to predict values instead of properties and text. And then we have representation. So basically, since we have a lot of different representations in chemistry, we here try to train the model on different representation and see how it performs. And then we also have inverse design. We know that we are predicting the property of the molecules from the molecules, but what happens if we inverse the process and predict the molecule from the property of the molecule? So this is what we try to test in the inverse design. And then we have stretch the limits. Here we are just trying to go beyond these tests, and we're trying to see if the model has some other capabilities, such as extrapolating. These are some examples or some representation of the methodology process. So you can see on the left-hand side, we have the dataset, which could be molecules or materials or chemical reactions. And then the tasks here, some of the tasks represented here are classification, regression, and inverse design. So for classification, we're given a question and we're given a model, and then we are trying to predict whether these models are low or high. And then we have the regression. So we're given the molecule, the structure of the molecule, and we're going to be predicting some value related to that molecule. And then in the inverse design, as we said, we're trying to inverse the question. So we are given a data point, or we're given, for example, a property or a number, and then we're trying to predict the structure of the molecule or the molecule itself. So now we go into the result and analysis and insight of these methodology. So first we talk about fine-tuning. So what we have found is that after fine-tuning the model and trying to train it on the data points, we have found that the fine-tuned GPT model uses only 50 data points in order to get the same performance of 1,000 data points in different models or the previous baseline models. So if we analyze that result, we see that it is working well. However, such fine-tuning requires expertise in order to be able to optimize it very well, because fine-tuning is not a random process. So you have to understand what you're doing when fine-tuning in order to be able to fine-tune a model effectively. So when we look at the insights, we see that fine-tuning gives us computational efficiency because we're using less data points and we're using less time when training the model and getting the same performance of different baseline models with more data points. Now we go into the classification. So we see that the results of classification is that it was able to demonstrate competitive performance with the previous baseline models, and it also sometimes required fewer data points. However, when we analyze the results, we see that sometimes this might be an exception where we have imbalanced cases of outputs, or if we have high data regimes, then the conventional models or the baseline models the performance might catch up to the GPT-3 model performance. So we see from the inside that using GPT-3 in classification gives us data efficiency in some points. However, we still have some limitations due to the fine-tuning process, which is causing us to have some issues with the imbalanced cases and the high data regimes. And then we go to the regression model. So we see that it was able to also achieve high performance in a regression task, even though it was kind of more challenging than classification. However, when we analyze the whole result, we see that it also had some exceptions in its result, as it required more data points tasks. And when it required more data points, then the performance is going to catch up with the performance of the baseline models. So here in the insights, we say that regression was basically more challenging than classification task, which is also why sometimes the researchers need to convert it to classification model before being able to use it. And then we can also see that because it was able to work on classification as well as regression, there is a sense of generalizability and adaptability for the GPT-3 model, so it is able to work on different tasks. Now we go to the second part of the result and analysis. So we have the representation. In more complex regressions, we have the IUPAC representation, which is the International Union of Pure and Applied Chemistry. And then we have the line encoding, which is the SMILE and selfies. In general, the model was able to work on any of these representations, and it was also able to give good performance. However, it was able to give the best performance using IUPAC names. This, in fact, makes it simpler for the researchers to do fine-tuning because most of the researchers use IUPAC names in their research. And it also gives us the interdisciplinary potential because it's able to work on different representations, which means that researchers do not have to keep changing the representation of the molecules in order to work with the GPT-3 model. As for the inverse design, so basically here we said that it was about inversing the question. So basically the researchers did say that it was successful. And when we look at the analysis of the result, it was able to successfully have novelty and diversity when generating molecules. So it was able to generate different types of molecules because it was able to also take different types of representation. And however, it also had some temperature sensitivity when generating novel molecules. So basically, this shows us the potential of GPT-3 in computational chemistry. Now we go to the last test that has been done to test whether these results were valid or not. So basically, they went out of their way to test whether the model would be able to have extrapolation and whether it would improve the skill of the model would be improved with iterative training. So analyzing the results, it did say that the model had extrapolation capability, so it was able to extrapolate. And then it also had good performance with small data sets. And then it also had some versatility. So now, as an insight, we say that it shows good potential for future work in chemistry, and it is very efficient and very accessible to all the researchers. However, it still has some challenges and opportunities because it requires iterative training in order to be improved, and it also doesn't work well for higher numbers of datasets. Now, when we look at the conclusion, so we have the first conclusion is that GPT was able to show remarkable capabilities in chemistry-related tasks, as we have seen before in classification, regression, and many more tasks. And then we have the performance. We have seen that the performance was very good with a smaller data set, but it also had some exceptions when being tested with higher datasets or higher dataset regimes. Now we also have the representation, so it was able to work with many different types of representations, and that has been seen with IUPAC or smiles and selfies. And then we also have, for the future, we see that this model might be able to have good potentials of being used in computational chemistry, and it might be able to open more doors for more research. And then we also finally look at the critiques and the remaining gaps. So when we look at the critiques, we have two. So first of all, we have the bias because the model was able to identify correlation, which is why it had shown good performance. However, sometimes these correlations are not meaningful, so there's an issue with the causative relationship between the prediction and the dataset. So this might need a little bit of more fine tuning. And then we also have some limitations because, as we said, that we need iterative training in order to improve the data set and in order to improve the model performance. And then we also need to fine tune the model to work with higher data sets and imbalanced classification cases. So basically, the remaining gaps would be the bigger dataset issue. How would we be able to use GPT-3 to work with bigger datasets? And then also the performance-wise, how to improve the performance by including more diverse and comprehensive training dataset, including the unsuccessful ones, without having issue with the performance in comparison with the baseline models. Thank you very much for listening. And if you have any question, you're welcome.